Okay, so here we are with lesson 6, and this is really starting the second part of our unit in energy. And so this little mini unit, it's 3 lessons, talks about thermal energy and kind of the beginning of thermodynamics. And so as often is the case in science, um, the development of thermodynamics really came about because two um, different scientists were doing different things, and they're kind of paralleling some of the work of the other. And those two scientists were, of course, Robert Brown and Albert Einstein. And their work in two separate areas kind of complemented each other. And when, of course, scientists then share information, say, hey, wait a second, what you're doing kind of makes sense to me, and what you're doing makes sense to me. And then we can make some great discoveries. So here were the two things that were totally crucial. I'm joined today by senior science student Thomas, and
Hello.
he's their peer tutor. And so two crucial things, and Thomas is going to take us through what they are.
All right, so the first crucial thing that came about was heat and how we define heat scientifically. And that is that heat is the energy of motion, or as we now know, the kinetic energy of matter at the atomic level. The second discovery was of the kinetic molecular theory, and this theory had three postulates. The first was that all matter is made up of small, constantly moving particles called atoms, and groups of atoms are called molecules. The second is that atoms and molecules exert forces on one another, and this keeps them a specific distance apart. The third is that the distance between molecules and the strength of these forces are what creates the states of matter, so solids, liquids, and gases.
And so it was because these two areas kind of came together that, wait a second, heat is this kind of kinetic energy at the atomic level. So all molecules are in motion, right? Small, constantly moving particles. Okay, well, wait a second. That right there implies that these things have kinetic energy. And so that kind of built into this idea, right? There are certain distance apart, distance between the molecules are the three states of matter. Oh, wait a second. The states of matter have a lot to do with heat. And so these two areas, it was like, wait, there is a major connection between these two areas. All right, so the specifics of the phases of state, solid, liquid, and gas, are left to you to kind of review because most of you probably know quite a bit about this. So what we want to do is your Nelson 11 physics textbook on page 288 kind of does a little brief summary, and you should fill in at this point kind of you can either press pause and do it now, or you can do it after the lesson, but a little bit of reading on solid, liquid, and gas and what those three states of matter are. Um, but we know, to summarize, that if molecules are moving around and they have kinetic energy, that kinetic energy has to come from somewhere. And so where does it come from? That's a big question. It comes from another type of potential energy that has a lot to do with electricity, and it's electrostatic potential energy. Thermal energy's got to take that into account as well.
So now we can consider temperature now that we've learned a bit about heat and how that's connected to the motion of particles. So if all particles in a sample are constantly moving, it's almost impossible to quantify the actual energy of any one particle because a sample could have billions or trillions of particles. So what we can actually measure is instead the average kinetic energy of all the particles in that sample, and we call this temperature.
Yeah, because if you've taken grade 11 chemistry, you'll know a little bit about Avogadro's number, and you know that in a sample of some substance, holy cow, there's a lot of particles in there. So you can't actually measure the kinetic energy, but temperature is this great thing.
So when a substance is heated, then its volume increases, and this is known as thermal expansion. And of course, we know this if we consider any state of change, such as a small ice cube melting. When it melts into a liquid, it can increase its volume, and it, of course, occupies a much larger volume. So thermal energy increases the kinetic energy of the atoms and molecules in a sample, and this causes an increase in the average distance between their molecules themselves. And so this is how a thermometer operates, and this is what allows us to actually measure temperature of a sample.
So there's 3 temperature scales that we know about: the Fahrenheit scale, the Celsius scale, and the Kelvin scale. Some of them you may be more familiar with and maybe even more comfortable with than necessary. Certainly Americans would be more comfortable with a Fahrenheit scale. We usually don't use a Fahrenheit scale in Canada, but this is, of course, named for German physicist Daniel Fahrenheit. 1736 was kind of the time about when this scale came into being. Of course, water freezes 32 Fahrenheit and boils at 212 Fahrenheit.
Yeah.
And sorry, go ahead.
And Daniel Fahrenheit actually calibrated all this using brine, which is seawater. So that kind of makes it different from Celsius, which we'll learn about in a second.
Yeah, so and that's why it's a little bit strange. A degree Fahrenheit is a little bit different than a degree Celsius. But Celsius is kind of probably the one that Canadians and, of course, most of the world are most comfortable with. Named for Anders Celsius. He was Swedish. And you'll notice 1744, so not that much later, but for a long, long, long time, the Fahrenheit scale was more popular. And now, of course, in the last, probably 100 years, the Celsius scale has become more common in most countries. It's usually the metric scale.
So as we know, probably most of us already know that water freezes at 0 degrees Celsius and it boils at 100. And so contrary to Fahrenheit, it was actually calibrated using distilled water instead of seawater. And so this last kind of temperature scale is called Kelvin, developed by William Thomson, also named Lord Kelvin. He was British, and this was developed quite a bit after the Celsius and Fahrenheit scales in 1904. And William Thomson hypothesized this theory of absolute zero at 0 Kelvin, where there is no motion of molecules, and there's just no particle motion. And
that would kind of suggest like a low, like a bottom floor for temperature. So if temperature is the molecular motion of molecules, well, there's nothing lower than just no molecular motion. And so what that would be is that would suggest kind of like this bottom floor for temperature. And that's what he hypothesized. And we say that absolute zero is 0 Kelvin. That is the lowest temperature that we can get. And it actually happens at 273.15 degrees Celsius below zero. So it's very, very cold. There's, of course, no upper limit necessarily to temperature or nothing really that we're going to talk about now, but absolute zero would be the lower limit.
So off to the right of your page, you can see that there's some conversion factors that'll be really handy to know when you're working through some questions, like we will in a moment, just for converting Celsius to Fahrenheit or vice versa, or Kelvin to Celsius.
Oh yeah, it is important to note, sorry, just before we go on, that the size of a Kelvin is the same as the size of a Celsius, okay? And the way that we write these, of course, you can see Fahrenheit, and we'll just kind of take this right here. Fahrenheit has the degree right here. Celsius has the degree symbol, but Kelvin does not. So as far as convention goes, 1 Kelvin does not have a degree thing here. But the size of a Kelvin is the same as the size of a degree Celsius, which is not true for Fahrenheit, because Fahrenheit are different size. Their gradations are different. Anyways, as we move on, here is example 1 for today. So day when the temperature is 50 Fahrenheit. What's the temperature in Celsius? What's the temperature in Kelvin?
All right, so as many of us know, 50 Fahrenheit's not a super nice day. It's not too cold either. But if we're going to convert this to Celsius, we're going to use this good conversion factor. We see that what is equal to there on the screen. Now we can sub in our degrees, and we get that 50 Fahrenheit equals 10 degrees Celsius. Now, to calculate Kelvin, we can use our degrees Celsius that we just found to calculate Kelvin. So there's our conversion factor. We sub in, and we get that 10 degrees Celsius equals 283.15 Kelvin. And remember, there's no degree sign on that Kelvin.
Yeah. And so if we want to round to sig figs, we can do that there. Thomas is exactly right with the units. Just make sure that when you're doing this, because sometimes, especially for those of you who still have a little bit of problem with solving equations, this is in brackets, so we got to do this first, and so on and so forth. All right. So moving on. Let's talk about thermal energy and how we transfer thermal energy. So this is a really good demonstration that we can actually do with you, even though we're here and, of course, you're watching this somewhere else. So wherever you are, kind of find something like the surface of your desk or something that's wood or something that is, around you that, um, is kind of like a plastic or something like that, and place your hand on that. And of course, note the warmth of that surface. Now place your hand on something that is metal. So perhaps the leg of the chair that you're sitting in or some metal object that's around. And of course, which of those two objects, the desk or the chair, is warmer? And right now, we could actually do this here, and we could do this here, and like right now, we've got an overhead projector, and we're grab the arm of the overhead projector, grab the surface of the desk, and we say, okay, yeah, so definitely the metal overhead projector feels colder than the desk, and of course, well, yeah, the surface of the desk feels warmer, the metal feels colder, but really, is it warmer or is it colder? And so when you think about this, your desk and the chair, or in our case, these two objects, they've been in the same room for hours, so they have to be at the same temperature. So why does the chair feel colder than the desk?
So this can be answered just through some basic information about the human body, and that our bodies don't actually measure temperature, but we only perceive the flow of heat in and out of our body. So there's not really a hot or cold, just an excess of heat. So we can feel the metal being colder because that metal is drawing heat away from our hand much faster than the surface of our desk.
And so that's one of those interesting things. Some things insulate and some things conduct heat. And we'll talk about the difference between materials in a couple of minutes. So we've learned about the conservation of energy. Can't be created, can't be destroyed, just transferred from one to another. So how does that fit with thermal energy? Well, James Joule, in the mid 1800s, the guy who we named a unit of energy after, he did this really interesting experiment where he had these masses attached to pulleys and then eventually connected to these fins, these paddles that were in water. And so he moved this gravitational system, this gravitational potential energy, up and down, which spun this pulley, which of course turned the paddles. And what he recorded was that with this repeated kind of motion where we turn gravitational energy into the motion of water, that the water heated up just a little bit. So he was the first one to show that gravitational potential energy could be converted into heat energy.
So, in your textbooks, you're going to explore the methods of heat energy transfer, and some of these might be a little bit familiar to you. It's on page 276 of your Nelson 11, and obviously we can think about our kitchen when we look at these three different um, categories. So, conduction, when we think of conduction, what do we think of in our kitchen? Of course, we think the stovetop. There's a piece of metal that becomes very hot, and that transfers heat to our metal pot, and that metal pot gets really hot and transfers the heat to our food. Next is convection. When we think of convection in our kitchens, we might think of the oven, and these are air currents that heat the food, so the air currents get really hot in our oven, and this is, of course, what allows us to heat up our food. Then radiation, the last one. When we think about that, we might think of our microwave, which is a little bit more complicated with waves, hot spots, and cold spots, but you can read about that in your textbook.
Cool. All right. So now what we can do is we're talking about this thermal energy, and we're about getting ready to quantify it. And you can see down here that we're getting close to coming up with an equation. So we'd like to be able to, to quantify this notion of heat and heat energy. So the transfer of heat energy depends on three things. So it depends on the difference in temperature between two things. So heat will flow between two things that are really at vastly different temperatures a lot easier. Heat will flow really, really quickly. The mass of the substance, so heat will flow into objects that have differing masses. And then the type of substance, which we already alluded to a little bit, these three things play a role. So first of all, the temperature difference. If the temperature difference between a hot and a cold substance is increased, then more heat will flow. Okay, so that's the first thing. Mass of the substance. If a substance has more mass, it has more molecules to transfer thermal energy. So if something has more stuff in it, it's got more molecules which are vibrating more, which can then transfer more heat. And last but not least, the type of substance. So different substances will accept heat transfer to varying degrees because of their chemical nature. So some things are conductors, some things are insulators. And the classic example of the type of substance, there's actually a holiday movie. It's where a kid sticks his tongue to a metal pole. And of course, what happens when you stick your tongue to a metal pole is that it freezes to the metal pole and then gets stuck. Um, and of course, the reason why is because there's a ton of mass in that metal pole, a lot of mass. And so there was a lot of molecules to accept heat energy from the tongue. And then, but also, if the pole had been made of something like an insulator, like wood, then of course it wouldn't have been able to have heat flow quite as quickly or quite as rapidly, and maybe eventually would freeze, but it wouldn't freeze instantly because wood is not as good a conductor. So this concept of specific heat capacity is the amount of heat energy that's needed to increase the temperature of 1 kilogram of a particular substance by 1 degree Celsius. So from there, we get these three quantities. And now Thomas is going to kind of take over and explain the equation.
So these three quantities will lead us to the equation below, which is that the amount of heat that's going to flow is equal to the mass times the specific heat capacity multiplied by the difference of the temperatures, where the mass is in kilograms, specific heat capacity is in joules per kilogram Celsius, and temperature is in, of course, degrees Celsius. And when we multiply all these three things, we get energy in joules.
Okay, so this C, this specific heat capacity, this what is this? Where does it come from? Like, is this like we've talked about mass and mass is right here. We've got delta T and delta T is up here. So this specific heat capacity, does it have to do with the type of substance?
Absolutely, it has everything to do with the type of substance. As we've already kind of tested in our thought experiment by touching the metal and the wood, we can see that certain substances transfer heat more readily than others. So just like we've defined specific heat capacity above, C is specific heat capacity.
Yeah, okay. Yeah. And it's like a constant then, that for like brass would have a specific heat capacity, and say aluminum, it would have a specific heat capacity. So it's all very, like C is a constant of nature, just like say the density of an object would be a constant.
All right, so now we're going to do a couple examples using specific heat capacity. So in this example, we're going to look at how much energy it takes to raise the temperature of a 1 kilogram piece of copper pipe from 25 degrees Celsius to 66 degrees Celsius. And we're given a specific heat capacity there. So we're going to start by listing what we're given. We know the mass, the temperature difference, and our specific heat capacity. So now we can use our equation. Oh, there's the delta T there by calculating it. Mm-hmm. And our equation delta EH equals MC delta T. We can sub in our values and multiply through, and we get that it takes 2 times 10 to the 4, or 1.6, joules of energy to raise the temperature of this copper pipe.
So that's like 20,000 joules. That's a lot of energy, right? Like that's a significant amount of energy in comparison to the energy that we've been talking about, gravitational potential energy. Heat is a huge source of energy. So if you think about, say, water that's running through your pipes, and you have this hot water pipe, and this water, if it cools down, right, this pipe you could in fact lose, if you lost this much energy along the way, the temperature of the water in your pipes could go from 66 to 25. Like, this is a lot of energy to lose, and that's usually why our pipes are insulated. Anyways, go ahead.
Here's example 3. So a kind of a similar question, but we're going to look at it in a bit of a different way. So we've got a 0.5 kilogram block of iron, which is originally at 80 degrees Celsius, and it's going to be cooled by removing 2.28 times 10 to the 4 joules of heat energy. Now what we want to find is the final temperature of this block. Mm-hmm. So we can start by listing what we're given. We know the mass and the specific heat. Now delta T is a bit different now because we don't know the final temperature, but we do know the initial. So we can start by listing it out, saying that we don't know T2, but we know T1. But we also know EH, so we still only have one unknown.
Now you'll say, yeah, okay, sorry. Explain why this is listed as a negative.
Mm-hmm. So This is listed as a negative because we're going to be removing heat from the system to try and cool down the block of iron here from 80 degrees to whatever T2 is going to be. Right, we're removing heat from the system.
It's like we're doing negative work. So we got it negative because we're taking that heat away.
So now we can start with our equation. We can sub in our values here, and you see we have to actually put T2 minus T1. Then we can collect like terms and rearrange, and we'll get at the end that T2 equals negative 19.1 degrees Celsius, which is a very big temperature change. Yeah. So what this is initially saying in total is that if we were to remove about 20,000 joules of energy from an iron block that's at 80 degrees Celsius, which is pretty hot, it would drop all the way down to negative 20 degrees Celsius. So it's a big jump.
Okay, there you go, lesson 6.